Hello again, Greg Beals. We're going to tackle ionic compounds. This is part 2. So if you're looking for an introduction, going back to part 1, but we're going to dive right into naming and formula units and start to put all the pieces together on ionic bonding. So when we start writing formulas, and that's what we're going to jump into right now, there's 2 steps really. First thing we need to do is look up the oxidation state. Okay, the oxidation state is the charge an atom will have when it turns into an ion. Well, how do I find the oxidation state? You need to have a good periodic table, and then you need to look at the key and figure out where is the oxidation state on here to show me what ion it's going to turn into. I'm using Wikipedia here in the Wikimedia Commons, and you can find some really great stuff there. I'm going to use calcium as an example here. I've blown it up from that periodic table, and you can see the little number that we've got over here, the +2. Again, you're just going to have to figure out, well, my periodic table, where is the oxidation state located? And for calcium, it appears that the oxidation state is +2. So when calcium turns into an ion, it's going to be calcium with a 2+ charge. What does that mean? It means when calcium turns into an ion, 2 negative electrons go floating away. That's how it turns into a positive charge. What about oxygen? If I look at oxygen here, it's got a whole bunch of them, but I'm going to teach you how to deal with this in a little bit. The most common one is the -2. That means when oxygen turns into an ion, it grabs a hold of 2 more electrons which have a negative charge, and now the whole oxygen has a -2 charge. So we've just built 2 ions. Now we know from the introduction that I did on the last, or maybe you don't, go back and watch it if you don't, that ions, a positive ion and a negative ion, will be attracted to each other and they will glue themselves together with an electrostatic force. So once we've figured out the oxidation energy, step 2, we need to add the superscripts to balance the charges of the ions. The calcium was 2+, oxygen -2. Those two are going to even each other out when they combine. The charges are going to even each other out, which means we end up with CaO. This is calcium oxide. Let's practice a few of these. I'd encourage you to get out your periodic table, find the oxidation state, and just see if you can get all these correct here. And nitrogen, go ahead and find it on your periodic table. Nitrogen is a tricky one. It's got a whole bunch of oxidation states. Well, how do I know which one to use? That's a common question I get in my chemistry class all the time. Now, I'm going to show you the simplest way to figure out, well, which nitrogen would I use? In beginning chemistry, this is how we go through the process. All right, I'm going to find nitrogen on my periodic table. It's in group 15, also called group 5. And that means that even though it has several oxidation states on here, it still has 5 valence electrons. So I'm going to write that. So there's our 5 valence electrons. Now nitrogen, like all elements except for hydrogen and helium, would like to have 8 valence electrons, which means nitrogen's going to go out and steal 3 more electrons so that it has a full octet. If it does that, now it's got 3 extra electrons, and electrons have a negative charge. So what's the common type that I'm going to use? Nitrogen with a -3 charge. So now we can start to put these together. Hydrogen had a positive charge and fluorine had a negative charge. Those are going to balance each other out, which means I get HF, which would be hydrogen fluoride, but it's actually hydrofluoric acid. We'll learn more about that later on. Next one, magnesium, we looked that up. It had a 2 positive charge. Let me grab a pen here. And oxygen had a 2- charge. That's going to even each other out, which means we get MgO, magnesium oxide. Aluminum, it had a 3+ charge, and nitrogen, we decided, had a 3- charge, so we get Aln, aluminum nitride. Moving on. So I showed you our example with nitrogen, sort of what to do when we have ones that have more than one option for an oxidation state. Not all of them follow that nice common trend, like would be nice and easy. So I want to use that as my disclaimer, although I'm not going to go into it right now. We'll get into it a little later on. I want to keep it basic, and then I want to jump into polyatomic ions. But that's just my little disclaimer for now. We will get into it more later on. Okay, part 3 for ionic compounds. This is naming ionic compounds, when you start to put them together and name them with the formula units. And I've got 4 rules that I like to use to teach this concept. Now, when I'm teaching it, anything that has a box around it is incredibly important. It's something you're going to use throughout all of chemistry. And 3 months from now, when you've forgotten, I can't remember, you can always flip back and find anything with a box around it and remember, hey, this was the stuff that was important. So this has got a box around it. Obviously, it's going to be important. Rule number 1 for naming ionic compounds. We always start with the cation. So the cation is the first one. It's the positive one, and it keeps the name of the metal. For example, calcium, when it ionizes, is going to make a positive ion. So calcium 2+, we call that the calcium ion. Nothing changed about the name. Then, after that, we'll put the anion. The anion has a negative charge, and we change the ending to "ide." Now, these are just basic, simple ionic compounds or formula units for now. So we looked at chlorine. Chlorine, when it ionizes, makes a negative charge. That makes a chlorine or the chloride ion. So when I put those two together, I get CaCl2, which is calcium chloride. Now, if you're wondering, so very quickly, if you're wondering why we have this 2 down here, well, we have calcium with a 2+ charge and we have chlorine with a negative charge. Those don't even out. We're going to need 2 chlorines, 2 of those negatively charged chlorines, to even out that positive 2 charge with calcium, which is why we get CaCl2. So look here, we're moving along already. Let's go to rule number 2, again, a box around this. What do we do with those metals that have multiple ions? So sometimes they have multiple oxidation states. They can turn into lots of things, especially the transition metals. Transition metals, if you've forgotten, live down here in the Grand Canyon in the valley. What do I do about those? Well, I pulled cobalt out of here just as an example. Cobalt's 2 most common oxidation states are cobalt with a +3 charge and cobalt with a 2+ charge. So I need to say which one is used in the formula unit. The way I do that is with these Roman numerals down here. So this cobalt 2 tells me that it's cobalt with a 2+ charge. It doesn't mean there's 2 cobalts. It just means it's the cobalt with a 2+ charge. If we had cobalt 3+, we would write cobalt 3 ion. Sorry for the mess, but there's your example. Sodium, we've already looked at it. It's going to be the sodium ion with a plus charge. Calcium, because there's only one option for calcium when I look it up on the periodic table, and that's a 2+ charge. When I look up aluminum, it only has one option for an oxidation state, so I don't need any Roman numerals. It's going to be the aluminum ion. But when I get to iron and I look at iron, it says iron could have an oxidation state of 2+ or an oxidation state of 3+. So I need to say which one I'm using. And obviously, because it has a 3+ right here, it's the iron 3 ion. Down here, this is the iron 2 ion. I find lead. Lead's got several options as well, right? It's got an oxidation state of 2 or 4. So I need to say which one I'm using, which is lead 2 ion. And finally, silver, I looked that up. Oh, silver only has one oxidation state. So I don't need to say which one it is because there's only one option. It's silver with a positive charge. And a few more just for practice. Chromium has a couple options. So chromium 2 ion, chromium 3 ion, and platinum has several options as well. So you got to say which one it is. Next concept are polyatomic ions. Believe it or not, polyatomic ions end up being more common sometimes than the regular ions. Now, poly means many, atomic means atom, and ion means ion. So pretty self-explanatory. Here's some examples of polyatomic ions. Okay, phosphate is a phosphorus with 4 oxygens hooked to it, and in order for that to build, it needed 3 extra electrons. They have a negative charge, so the whole thing, PO4, has a -3 charge, which means PO4 is going to go out and attach itself to positive things until it's evened out that negative charge. Carbonate, carbon with 3 oxygens hooked to it, the whole thing's got a 2- charge. It's going to go out and attach itself to things with a positive charge until it's evened it out. Acetate, same story. These things live together. I like to say they live together and they float around and they hunt out positive things to attach to. They don't break apart, they just attach like they are. The charge that you see on there is for the entire group, and these often end in ate or ite. We'll learn more about that coming up, but it's important. If you don't see "ide" at the end, we've been talking about "ide" every time. If you don't see "ide" at the end and you see ate or ite, man, that throws up a red flag in my brain that it is not just an element, it's actually a polyatomic ion that I'm dealing with. So where can I find the polyatomic ions? On my periodic table here, there is a table on the back, on the bottom, and the middle. And it's one of the most important tables we use in my chemistry class. Okay, it's on the back, on the bottom, and the middle. But likely you don't have a periodic table that has them on the back, on the bottom, and the middle, so you're going to have to go out and find them. This one is right off of Wikipedia. So literally a really good list of the anions and how they're listed with their names. It's also got a list of the cations. I just didn't include them there. You're going to need to get a list. Either you print it out and keep it with you, save it on your digital device. It's going to be a lifesaver for you. Now, a couple rules. I've got them listed on here. You just need to get to know these. The quicker you get to know them, the better off you're going to be. Which takes us to rule 3, the oxyanions. Oxyanion means it has oxygen. Anion means it's a negative charge. We're going to examine when nitrogen and sulfur bond with oxygen. So rule 3, how do I name the oxyanions? Now, sometimes when they bond, you'll have one option that has several oxygens. You'll have one that has fewer oxygens. So chemists came up with a nice way to keep track of these. When nitrogen and oxygen bond, those are the two options that can pop up. Okay, NO3- and NO2-. So the first one is nitrate, 888, because it has more oxygens. The second one is nitrite, because it has one fewer. So now you can start to see why this naming is important. If you get the naming down, you know exactly what the composition of that molecule or that formula unit is. Same thing with sulfur. Notice it's SO4 2-, but it has more oxygens, so it's sulfate, and the one below it, SO3 with a 2- charge, is sulfite. Now, what about the oxyanions that are bonded to halogens? Halogens are group number 17. You can see it right up there with the yellows in it. It gets its own set of rules, and the main reason is it can make several options of oxygen hooked to it. So the one, whichever one has the most, has a prefix per and a suffix of 8. This is all going to make sense when I show you examples on the next slide. So just bear with me. Again, it's in a box. Write it down. Hang on to it. You'll need it throughout chemistry for as long as you take chemistry. The one option of oxygens with the halogens, it has one less, is 8. One less than that is ite. And then the fewest is hypoite. So the per is like hyper, but they shortened it because we're all too hyper to write the HY. I don't know. But per and 8, and then the least is hypo with ite at the end. Examples. So we've got ClO4 with a negative charge, ClO3, Cl2, and ClO at the bottom. 4 different options that can form when a halogen and an oxygen start to get together. So the one that has the most is going to be per-chlor 8. Okay, the chlorine and the oxygen is 8. It's got the most, so it's per. The next one below that, that's going to be chlorate. The one below that is going to be chlorite. And finally, the one below that is hypochlorite. Really pretty self-explanatory. If you can figure out one of them, like chlorite, you should be able to work your way up or down the scale. So really, those are the rules. That's the important stuff. I'm going to do some practice on the next couple screens. You can follow along, practice them, grab your periodic table, or you can just check your answers and zoom your way through. It's entirely up to you. All right, so some simple ones going back to the beginning. Sodium sulfide at the end. What about CuO? Well, copper, when I look it up, has multiple oxidation states. It could be copper with a 1 plus charge, or it could be copper with a 2 plus charge. Well, let's take a look. We don't know which one we use. So let's go over here to oxygen. Oxygen, when I look it up, always has a 2 minus charge. So I'm going to put the 2 minus here. Now, if there's only one copper and only one oxygen in our example, well, then copper had to have a 2 plus charge because there's only one copper and only one oxygen. They had to even each other out. So we know that this was copper with a 2 plus, which means what was the name for that? That's copper 2. Don't forget the 2. It tells us which one we used. Oxide. So what about CoCl3? Well, CO, I look it up on the periodic table, right down here, number 27, and cobalt has two options. Cobalt could be cobalt with a 2 plus, or it could be cobalt with a 3 plus. Now, I'm going to go look at chlorine because I don't know which one to use. I look up chlorine on the periodic table, and chlorine is always a 1 minus. Well, if I needed 3 chlorines down here, that would make 3 negatives, which means this cobalt must have had a positive 3 charge, right? Because 3 negative chlorines would be 3 negatives, and I had it evened out. So I've got to have cobalt with a 3 plus, and chlorine always has a 1 minus. Move the 3 down here. Let me rewrite it. I've got CoCl3. This is cobalt 3 chloride. Sorry for the horrible handwriting. It is what it is. What about CuS? We've already determined that Cu, or copper, down here can have multiple oxidation states. Sorry, down here it could be copper with a 1 plus, or copper with a 2 plus. Now, sulfide, or sulfur, when I look it up, can have a 2 plus, a 4, or a 6 plus. So how do I know which one to use? Well, I don't know which copper to use, and I don't know which sulfur to use. I always like to go over here to the anion first. Here's why. Sulfur, when I look it up, sulfur is in group 1, 2, 3, 4, 5, 6, which means it has 1, 2, 3, 4, 5, 6 valence electrons. And it wants to grab 2 more valence electrons to have a full octet, which is going to give me sulfur with that's a 2 minus charge, I apologize, with a 2 minus charge because it grabbed 2 more negative parts. And that's going to be the most common kind of sulfur that I need. All right. Well, if I needed 2 of the coppers, which says 2 right here, to even out with the sulfur, this must have been copper with a 1 plus, because 2 copper with a 1 plus to even out that 2 minus. So I have copper 1 sulfide. All right, we're on a roll. One more of these. Fe2O3. I find iron on here. Iron can have a couple different options. It could be Fe with a 2 plus charge, or it could be Fe, or iron, with a 3 plus charge. So again, I like to come over here to the anion. I look up oxygen. Oxygen's always going to be a 2 minus. And look, there's a 2 over there. Now, if I do the rule where I'm just crossing these over, which this is a trick, then this would have to be a 3 plus over here to move down there, and that would have to be a 2 to move over there, which means this has to be Fe 3 plus and O 2 minus. Well, what does that mean for naming? That means I used iron 3 and oxygen, so iron 3 oxide. All right, there's a few more up here. I'm going to write the answer down, so if you want to pause it and practice them and check your answers, pause it now and click on the next one. I've got the first 2 up here. Sodium and iodine are going to even each other out, which means I'm going to have NaI. Silver and sulfide, 1 plus, 1 minus, that's going to be AgS. And I wanted to check more closely on this one. When I look up barium, barium's got a 2 plus charge, but then I end up with sulfate. Now, I always run into the problem where people think that's sulfide, they look up sulfur, they move on. But it ends in 888, which means it's a polyatomic ion. On my table, it's on the back, on the bottom, and the middle. You're going to have to look it up if you don't have one of those or one of these. And the sulfate ion is SO4 2 minus. SO4 2 minus. Now the 2 minus and the 2 plus still even each other out, which is going to give me BaSO4. I have to leave that 4 with it because it tells me I have 4 oxygens hooked to that sulfur. Let's go take a look at the lithium. Okay, lithium is a 1 plus, and sulfide is sulfur. Could have a 2 plus, a 4 plus, or a 6 plus. How do I know which one to use? Sulfur's in 1, 2, 3, 4, 5, group 6, which means it has 6 valence electrons. It wants to have 8. If it has 6 now, it's going to grab 2 more electrons to make 8. So sulfur is going to have a -2 charge. To even those out, I need 2 lithiums for that sulfur to even it out. The last one here is sodium hydroxide. We've looked at sodium 1,000 times. It's a 1 plus charge, but hydroxide, hydroxide's a goofy one. It ends in "ide," but it's a polyatomic ion. It's actually OH minus. So when I put these two together, I get NaOH. So for these, you're going to see all of them pop up on the screen here, and then I'll come back and help you combine them to make the formula unit. So I've got them all on here. Now we just need to put them together. Calcium 2 plus charge, nitrate with a negative charge. That means I'm going to need 2 of those nitrates. So I'm going to have calcium, and then I'm going to have NO3, but I need 2 of those. So what do I do here? Well, I need to show that I have 2 of those nitrates, and I use parentheses to do that. So be very careful here in keeping track of these. All right, tin. It was tin4, which is why I put the plus up there. So I'm going to have SnCl. I'm going to put the, I know I need 4 of these negative chlorines to even that out, so I've got SN4. Next one down here, copper and carbonate, but here's the thing you got to be careful of. Look here, that's the cation and that's the anion. So I've written them out backwards, and you got to write them out in the correct order. So this is going to be copper carbonate. Be careful there. Again, the cation has to go first. Finally, BABR. Let me show you a trick here. This will work with any of them. If barium's got a 2 plus and bromine's got a 1 minus, I can take any of these superscripts and move them down to the other one for the subscript. So this is going to be a 1 and this is going to be a 2, which is going to give me BA. I don't need to show the 1. BR2. That'll work for any of them. So a little trick for down the road. We could have used that up here. You can use it anywhere. And last but not least, we've got the tin 2. I knew it was tin 2 because it says 2 right here. SO3, tin sulfide. Tin 2 sulfide. So this is our ionic naming. Really, the more practice you do with this, the better off you're going to get. Just keep working your way through them, finding examples, practice. Once you get this down, it's something that people rarely forget. You might just need a refresher. So I think you've got it down. This pretty well takes you through ionic bonding. We've got a few more things to cover, and those will be coming up. But good luck and keep on learning.